Hello, Arun.
Sir, wait for 1 minute, sir. 1 minute, 1 minute.
Okay, fine.
One more minute. One more.
No entro.
So, good evening to one and all present here. So, today we are moving into the third day of this 3 days faculty development program on VLSI technology and hardware for AI and ML. And today's chief resource person is Dr.R.Sakthivel, and he is from VIT University. So before going into this session, I will give you a brief note regarding Dr. Sakthivel, our chief resource person. So Dr. Sakthivel received his VTech degree in electrical engineering from Madras University in the year 2000 and his MTech in applied electronics from the same university in the year 2004. He has received his doctorate degree in the area of low power VLSI for high speed architecture development for signal processing and cryptography. Now, he is currently working as an associate professor in the School of Electronics Engineering at Vellore Institute of Technology, University, Vellore. His research area includes low power VLSI design, developing high speed architecture for cryptography, analog VLSI, and he is a member of ISTE, SSI, and VLSI Society of India. He is the co-author of the Basic Electrical Engineering, published by Sonarsti in the year 2001, and he is the author of VLSI Design, published by S. Chand in the year 2007. He has also published several technical papers in the national and international conferences and journals. He has delivered around 50 guest lectures, invited talk, and hands-on workshops in the areas of FPGA-based system design, analog IC design, full custom IC design, RTL to GDSI. So, based on his experience, he had nearly 8 years of industrial experience and 12 plus years of academic experience. He had conducted nearly 40 workshops in the areas of VLSI in different colleges in South India. He had delivered more than 20 invited talks, and he had also created 3 labs on his account. One is with respect and he had also created a lab named Cadence Analog System Design Lab, which is supported by Cadence Bangalore. and another lab by FPGA SOPC lab supported by Ultra Bangalore. So, this is the brief introduction regarding our chief guest, Dr.R.Sakthivel. So, this is our final session on this 3 days faculty development program. I once again thank all our participants to actively participating in this 3 days faculty development program. I hand over this final session to our chief resource person, Dr. R. Sakthivel sir. The session is yours, sir.
Very good evening. I request the part. Hello. Do you all hear me?
Yes,
Yes,
sir, no problem.
okay.
You can go on.
Okay, fine. Hearing my voice. Is there any echo? Arun? Professor Arun? Hello.
Carry on.
Professor, I hear an echo sound. Do I need to exit or?
No, sir, not good.
But I hear an echo. Whatever I speak, just to turn out. Hello. I think I have.
All the audience audio are in mute only, sir. No problem.
Okay, one minute. Professor Arun, could you hear me now?
Yes, sir, no problem. No echo.
Okay, fine. Right. Okay, thank you. Very good morning for a beautiful introduction. Thank you, Professor Arun Shekhar. Right. So today's session, I plan to go. It's little bit of a composite of many different domains. So I believe you could see my slide sharing. Just acknowledge me in the area of chat section so that if you have any queries, I could immediately take it. Or if you don't hear me, you can just put me a word in the chat box. I think everyone could hear me, right? Shall I move, Professor Arun?
No problem.
Yes. Okay. Okay. So, in fact, the whole idea of this particular session, I'm trying actually to cover a multiple domain. Probably it may be a composite of a little bit of biological science, biological neuroscience, a little bit of mathematics, a little bit of computer science, and some portion with respect to electronic circuits and VLSI. So I'm just my whole intention is to take you through different perspective of or the real hardware involved for the machine learning and artificial intelligence. That's my whole idea. So couple of slides we will look into what is the need motivation behind this, then we will see some amount of neuroscience and how this neuroscience is trying to reflect in the circuit building, what this AI and ML algorithm is doing, how are we trying to create a hardware for those architectures, and how are we modeling the neuron behavior in this. So all over my slides I am just using the slides for neurocomputational science by Rajesh and a couple of different websites. I would like to acknowledge them. And I am also using the slides, some of the slides from deep learning by Andrew Ng, and a few of the slides from different sectors of websites and different books. So most of the drawings may not be mine, and then and there, in fact, most of the area we have acknowledged the Wikipedia and all those things, right? So let's go about with a simple analogy like this. So, what do you think, or someone from the other end can respond to me? Raja Raman, sorry, mute your mic. Okay. If someone needs to stop me in between, maybe you can switch on the mic. Otherwise, please put your mic in mute. Okay. Right. So, the biggest thing in the human body, or the most ununderstandable portion of the human body, is my brain, or is our brain, right? Now, if you see the whole paradigm shift of the computing, you could understand one thing. First of all, what we did is, to reduce the human work, we went on with machines. Then certain areas, the human need to be beside the machine to take some decision or to act appropriately. So what we thought of making some sort of automation. Like, we went on with giving some sort of flexibility in decision making towards the machine itself, based upon the occasion which it decides. Say something like this. I have an electric oven. So when the temperature rises above 100, it automatically gets tripped, or the temperature need to be maintained accordingly. So some sort of a self-control mechanism we try to plan accordingly, and we installed all those options in the machine. Day by day, this becomes a slight improvement in that, and it went on with something called as IoT. Means now the machines start communicating with each other as human beings. Like, a group of human beings are there, they communicate with each other, they make a decision, they transfer their ideas, they transfer their views. So very similar to the human being, this ideas has been taken to the machine side also. Now all the non-living start communicating among themselves. The beauty is they also started communicating with the human being. Now we develop a mechanism in which the coexistence or the interrelation between the non-living and the living become so cordial, and they can easily coordinate with each other. Say I'm just saying reduce the volume just by my voice call. Automatically, the sensor present in my TV start detecting that, and it start decreasing the volume. Or I am saying switch on my fan or switch on my AC, or whenever um, I give some voice command over that, it start interacting towards me. Moreover, I am day by day instigating or installing certain amount of intelligence on all the missions and incorporating all the non-livings with certain amount of intelligence and connecting them. I call that as an IoT. Now, this has still improved a lot where it has moved to the next domain. What we say is making a machine as a human being. The whole idea of the neurocomputing or neuromorphic computing, things like that, what are we trying to do today is at the maximum, we try to see the whole brain of the human being is being transferred to the machine, and the machine should be in a position to take all sort of decisions that a normal or highly intellectual human being could take a decision at that particular occasion. So saying that it's not that easy. Philosophically, the most intelligent human being on the earth are the humans, are the most intelligent living being on the earth is human being. Now, almost the whole idea of this this paradigm shift is trying to mimic complete human being on a non-living behavior. In fact, this is more useful at multiple places, and what could be the other consequences is debated, and still that goes on. We don't know where it will. I get some. One second. Yesterday feedback link, since I am unable to fill it. Okay, right. Otherwise, I believe all are following. If someone could not follow, please put me in the chat box. I could see. Right. Right. So the whole idea is making machine as a human. That's what, while I was writing one article, I have mentioned something like this. You know, the machine uh, transforms itself to human, whereas the human transforms to a machine. This you could see in the day-to-day life. Almost the human life becomes so routine. Now, most of the cases, now the human being shed out some of the emotions attached to him, and he started working like a machine. Whereas now you see the whole transformation is trying to change the machine to a human being, or indirectly the next generation is only to make all machine to act as a human being. So on the other end, what could be the other effect of that? It is debated in a separate discussion. I don't want to get into that, but now let's see how to make a machine as a human being, or what is the need for it. So the present scenario is you need a huge amount of data to be processed, that too in online. A big, today you need a very huge volume of data that need to be processed in online, and that is supposed to be given without any time delay. And this process need to take place in the real time. So such huge amount of pixel processing need an enormous amount of computational power of the processor. So the need to develop a huge, huge computational processor becomes the need of the hour. And yes, machine learning plays a very important role with respect to computer vision, speech recognition, gameplay, medical application. So all this area you could see, it's inevitable, particularly with the computer visions, right? Particularly while you say with machine vision, this also comes as a separate area where now the machine is detecting, say something like this. I want the machine to take care of um, automatic coke filling, right? So the coke filled is being passed through a computer vision. It just to see what amount of coke is being filled, whether it is half filled, it is empty, or it is at the right level. If not, it is supposed to detract the one which is in defect. So I am making the computer to have the vision which a normal human being does, right? So this area, in fact, it is a booming area. I could see many people working on this area of computer vision. By the way, I assume most of the people are from the teaching domain, students, and some from the industries. So maybe we can share wherever you have some contradiction in the idea. And let first you put a question in the chat box. Later on, we will take the question at the end so that the flow may not be get disturbed. Right. speech recognition, gameplay, medicine, all this. Again, with respect to medical application, this ML AI finds a very huge applications. I mean, a very huge importance because, say, particularly like cancer detection, prevention, prediction, right? All this, this ML plays, or deep neural network plays a very important role in the medical field. In fact, not only in deadly diseases prediction, it has an important role in the diagnosis areas too, early predictions. So, by the way, in medicine, this has captured a greatest extent the accuracy of prediction. All these things has given an importance for machine learning. Right. Now the question is, okay, many people are speaking about machine learning, and there are many people who works on this. What could be, or where is the hardware in there? Some people, in fact, this for some, right? This topic itself will be, some sort of a mystery. How come, where is the hardware? Why he is speaking about the hardware? Because all the computer science people, if you ask machine learning towards them, they will simply go ahead with a couple of algorithms, the standard machine learning algorithms. They use the tools and there's, some of the libraries from the TensorFlow, and simply they run that with the data sets available. They train them, and then some of the data will be used for prediction and learning. Then they will decide, okay, this algorithm works fine for me. And nowhere, why should I require a hardware for this? This would be the immediate question which comes out of it. But at the back end, actually, a dedicated hardware is sitting at the system or a high-end computing, where the processor need to be designed. As a VLSI engineer or any hardware engineers, right? They thought of, like, it is something like this. In your, if you go to your bank and say I am depositing the principal amount of 10,000 rupees for the 10 month, and the interest rate is this. He would have written a simple C program, but the person who works in the bank need not have any idea about what is there in the hardware, what type of processing unit is there, what is the ALU, what is the memory, where it is exactly storing, nothing. A simple GUI, you can simply give the principal amount and the number of duration, what is the rate of interest, that's fine. That is with respect to computer science. But as an hardware engineer, I look it in the other way. Okay, to make this computation, what amount of memory is being required? What sort of computation is required? If I am making this computation, what should be the speed of that computation? What should be the area consumed by that particular IC if I need to have gates, logic gates to compute or to perform such sort of multiplication, addition, and then storing the data. So as a VLSI engineer, we always think like this, right? So an enormous amount of hardware is being required as a system on a chip, or the whole system is being kept as a small chip, which require a massive computational power to be performed, right? So here the main thing is huge availability of data, a GPU acceleration, that you increase the power of computation, and this has been applied to the machine learning technique, where it's used for all the earlier discussion applications which we made. So most of the people, some people, work on this algorithms, like computer science people work on here, whereas the hardware engineers work on coming up with a good GPU design or accelerator design or efficient hardware design for AI and ML algorithms. Whereas this is a data collection, so this is purely a data science, where you collect a data, pre-process a data, and go with all sort of statistics applying on that, and then making that to be available to this particular GPU, right? Okay. So actually, the key metrics of the hardware, which I mentioned here, is the accuracy, programmability, energy, power, throughput, latency, cost. Of course, many people would have been associated with all this, right? I believe you might be knowing all most of the cases. These are the metrics on which we decide what sort of processor is required for processing a huge amount of data. Right? There are many GPUs right now from the CPU, we moved on with the GPU, particularly with the machine learning algorithm, where you require a huge amount of data processing. Particularly Intel, Nvidia, all this IC manufacturing companies, they have taken a huge step on manufacturing ICs with the next generation deep learning processors, right? Because uh, mostly it requires a huge amount of computation, which is a matrix multiplication, uh, matrix operations. So to do that, you require a huge amount of a drastic processing element that need to be followed. Right. This is again some of the specification of Irish. This is one of the processor which has been used for CNN network, convolution neural network. In fact, these are the specs which has been given. See, look at the performance. It is 33.6 to 84 GOPS, right? And the frequency of operation is from 100 to 250 megahertz. So you could see this processor has been implemented with the 65 nanometer. Of course, it's a little bit old again, because the processor which comes out later, I think Intel Logi processor is with the 22 nanometer, I think. And the whole IC chip is rounding up to 4,000 micrometer cross 4,000 micrometer. Now you could imagine a huge amount of data is being processed in this small IC, where it plays an important role at multiple places, right? Multiple applications. So the whole convolution neural networks, right, which is deep neural networks, has been kept inside this sort of processing units. Right. Then there is also tensor processing unit, particularly to process a huge amount of data from the Google. They also have it. Right. From the Intel, they have one more processor. This is brain-inspired AI chip. Because this has been this came out, I think, in 2018, I believe. You may cross-check in the 18 or at the end of 2017. So this processor was something to mimic the human brain, right? Loki processor, Intel Loki processor. This is brain-inspired AI chip, which is more or less computing or performing the computation very similar to that of the human brain. This we call it as a neuromorphic processor. This whole processor is neuromorphic processor. And the neuromorphic MEM resistor, those people who are working with MEM resistor, um, they find an important application with respect to neuromorphic computing, which means with respect to memory. So MemRest, a couple of my PhD students are working with MemRest, and we have even published two papers on that using MemRest for neuromorphic memory. In fact, these areas are quite new, and the scope for working on these areas are really large. The spec of this particular Loki IC is also available in the net, so you can cross check. Right. Yeah. So mostly in a machine, it always need to do some sort of applications with something like classification, prediction, all this. So majorly it could be used in different areas with respect to diagnosis, all this recognition, right? Genetic engineering. These are the areas where really these processes has played a very vital role. I have just given some sort of example to do this, particularly cancer detection, industrial robots, right? Nowadays, most of the work, as I said, in fact, there is an alarming news also. I mean, not alarming. In fact, it has started a couple of some 2 years back. I don't know how many of you read Anand Vedan. There was one article called Survivor, just to 6 to 8 months back. It was a series, right? I think it was around some 40 series, 30 to 40 series, which were speaking about what will be the next generation, or how does the next era will be there with respect to uh, this human development. In that, one thing is very clear, and with all the statistics given, it clearly says that more than 20 to 30% of the human work has been given to a machine, right? It may be in industry or in the different sectors of human servicing sectors, manufacturing sectors, diagnosis sectors, in different sectors. Now, most of the areas it has been, or the human intervention has been removed and it has been replaced by the machine. Apparently, you could see even in the airport, sometimes deliberately they ask you to walk for a couple of meters. This is being done only to find out. Okay, let's see. Okay, so so what is being done is uh, they ask you to deliberately walk, means to find out the emotions, what type of emotions, what type of behavior you show in your face, right? All this are being taken into account to decide whether is there any chance, what is the probability of this particular person being or involved in trafficking some of the goods or something like that, right? Or is there any possibility with respect to its travel issues, right? um, Visa issues, all these things. So most of the places, even some of the what I understand from that is many companies, right, all over the world in different companies, they involve such type of machine to in the process of hiring, means during the interview it start analyzing his behavior, his answers, and trying to give the machine, trying to give its own suggestion. What is the probability of his retention in a company if he is being recruited? How truthful he can be with his company? So it can list out a complete list of a detailed study of a particular person, right? So it is more reliable in the sense we rely more on the machine rather than the human being, right? So the authentication of the data given by, or the authentication of the result given by such prediction algorithms made by the machine in the recruiting section plays an important role in hiring a particular person for a multinational company. So what I'm trying to say is most of the places now the machine has replaced, or indirectly robotics has replaced in multiple sectors. And the days are not too far. And again, I think you might be knowing this, in China already it employed machines for news reading, for teaching, learning, teaching process, and multiple sectors, right? Gradually it is taking its upper hand in multiple domains. So particularly industrial robotics, they are in essential need of this robots with an intelligence, automation, all this, as I already said, multiple areas with respect to military, government robots. I think during the COVID-19 also, you could see many fancy robots coming up, right, in multiple sectors, particularly with the airport, things like that, to help people from different domains. And in space research and analysis also, robotics plays a vital role. In fact, by robotics here, no more, it's almost like a human mission. That's it. Right? Healthcare sectors, applications, all this. I'm just skipping up. There are many, no, innumerable number of applications. In fact, there was one book which was narrating this interesting phenomena. I would like to share that idea. So you could see there were people. Okay, you could see the book. Ultimate idea of that book is what does it says is over a period of human evolution, the human has been segregated based upon different category, something like this. Based upon the race, the human has been segregated among themselves. Based upon the caste, the human has been segregated among themselves. Based upon the wealth, you could see the people has been segregated. These were the segregations among human beings, like which is used to segregate the human race based upon different yardsticks over the human evolution for the 1,000, 2,000 years. the next segregation will be something like this. This is what the book says. The next segregation will be technically are the people who are equipped with the technology, the people who are illiterate with the technology. There will be two class of society in days to come, or at least for next 50 to 100 years. You could see two sector of human beings which would be at two different level. These two different level will be, one sector of people will be the people who know to use the technology and run in pace with the technology. The others, the technology illiterates, they are being considered as no a lower class of society. So gradually the segregation which is with respect to race, color, or no caste, religion, all this will get diminished, and you could see these two class of society will be there. Apparently, you could also notice that in your home, like you always underestimate. Say, suppose with the use of technology, your mother doesn't know how to handle that. You don't deliberately do that, but still you underestimate his efficiency or intelligence. No, you don't equate that to your friend, or who is competent enough with you, who can be equally enough to handle the electronic gadgets. So this will get this will get developed, and this becomes a two type of society. That's what it says. So you should be no indirectly it also gives you a hint that we are supposed to be in line with the technology, right? I'm just taking you through a very few, the first portion. I mean, this is the need which we have been discussing on. And I would like to take the second portion as the computational neuroscience. Right. A couple of slides I will be looking on to that. And further on, I will go ahead with a few more. This computational neuroscience, as I said, there are many online courses in Coursera and things like that. In fact, there are many books, good books to go ahead also. I'm just taking you through few things which will make you to think in this aspect, right? Okay. One more important point which I would like to instigate is this. Almost most of the projects, right, are the most of the works which comes out, it's mostly an interdisciplinary work. There is no concept of a person being standalone and doing his work. Almost all engineering has been fused among itself, and it's an interdisciplinary work. Say, for example, say some 15 to 20 years back, or 20 years to 25 years back, if I say car, naturally most of the people will think that it belongs to a mechanical department. On the other hand, if you say now, like a car, now you need to realize where is the mechanical part in that car, because the engine become an electric engine, solar, solar using the solar energy, and almost you use some 10 to 15 protocols, including communication protocols, and you use 100 to 200 microcontrollers for controlling the, starting from air pressure, fuel injection, direction, GPU, the multimedia inside, like audio system, video system, what you use inside. All this are being controlled by different processes, and again they are all being communicated among itself via around 10 to 15 protocols. Now you really need to think about where is the requirement for a mechanical portion in that. What I mean to say is, it's more like an interdisciplinary work, where if you have in your mindset that human brain or things are more towards biology, uh, the days are not so far where you deliberately need to know something on this computational neuroscience or your brain, right? So with that idea, I'm just quickly taking you through a quick walk on this neuroscience. First of all, as I said in the beginning of the class, um, when you take the human, in that the most complicated, most not understood portion of the human brain is the human brain. Sorry, the most ununderstandable, the most still, there are multiple things which cannot be revealed or which cannot be understood till date is, right, the human brain. In fact, some study, I don't know where exactly, somewhere people were saying only 20% of the human activity, human brain activity is being understood. Whereas if you take the remaining organ of the human body, I can go ahead and prepare the lungs, I can go ahead and prepare the heart, I can go ahead and prepare a kidney. In fact, you can mimic all this. Or we are in the evolution of doing that. You can take it in the other way also, right? So starting from all the body replacement in your different organ replacement in your body, you have achieved almost in most of the cases, except the brain. And if you could do that, that is what we are doing with the robotics, right? Um, so now, very quick understanding of the computational neuroscience, and in fact, the human brain plays in enormous computation. You can't even believe. As a simple example, I will tell you one scenario where you could understand how much very precise it computes and learns. Say, suppose I would like to hit a mango, right? At the feet of some, let me assume some 50, 100 feet, 25 to 50 feet height. I would like to hit a mango. So normally we used to do that. You pick up a stone and throw a couple of stones. First you do that, or second time you do that, third time you do that. Within some 4 to 5 hits, right? You could see you can hit that mango and you can get that mango. Now, you just think, if I want to make a model for this, how complex mathematical model need to be created? I am supposed to decide what should be the angle of the throw, what should be the force I need to give, what is the height, what is the speed, right? How far it is located. I need to create a model for this, right? And after calculating all that, if you launch a stone, then you could see at a particular point it is going to hit that mango and you will get the mango. But I can assure you, to do this, you may take even your whole lifetime to design a machine to appropriately make a couple of hits to get a mango. Whereas you think about the brain does this job within some at the worst case some 10-15 hits, right? At every hit you make, the brain makes a learning. At every hit, oh, it is going little bit around 2 inches above, so I need to correct it. It goes for a corrective mechanism. And again, if the speed is high, okay, or if the velocity, or I don't know, if the force is less, it appropriately increase the force. So a huge amount of feedback from the environment is given to the human brain, and all this has been taken from different portion of my human body via sensors. All this information has been given to my brain through a nervous system. Now the brain collects all this information and makes a decision. What position I need to keep, what should be the force I need to give, what should be the angle which I should supposed to give, what should be the velocity I'm supposed to give. But remember, all this takes place within a couple of minutes, and you release the stone. Now, this becomes a casual walk of our human life. But you think, I am just trying to create a machine for this, then you will understand what amount of complexity will be involved in order to get such a huge amount of computation. This is what. So the whole idea is to get a mimic operation of the human brain activity. That's what we are trying to do. In fact, there are many. In fact, those people who are doing research or they working in this domain, I am speaking with respect to hardware. In fact, there are some sort of biological studies going on with respect to hardware as an computer science engineer or a circuit engineer, you could see there are many models being proposed in this particular area, and there are many papers being published only to model the human brain neurons, right? Okay. And there are many experiments being carried, many interesting experiments being carried out. Now, just for an example, one simple example I will tell you. If you take a light bar, right, and just to show that before a cat, right, you may think that you are doing something. I mean, the cat is not noticing that. But remember, if you put an electrode on the the cat brain and try to analyze the brain activity, when you try to show a bar of light in front of a cat and try to study the behavior of the brain neuron of a cat, you will understand many beautiful informations. In fact, all this has been published as papers, right? You can cross-refer with some of the papers in the website. It is there. So when you keep a bar, the intensity of the spike, these are the spikes which has been generated in the brain of neuron cells in the brain of cat. So when you keep the bar as it is, it gives something like this pattern. When the orientation of this light changes, you could see the pattern in which the neuron pulse generate, right? It is giving a separate pattern which is not similar to the pattern which is being held over here. So for every orientation, every intensity of the light which is being shown before a cat, you could see different patterns being generated in the cat brain. And if you could appropriately analyze using the electrodes, brain electrodes, you could see multiple patterns. Or what I am trying to convey here is, every activity that is happening near you is being recorded in the brain, and the brain learns some sort of activities from that. This is what you could see the reinforcement learning. In the machine learning, you would have learned about this. Reinforcement learning. Basically, go to 3 chapters of that. Right? If you read some of the books, you could understand, starting from different portion of the brain, what are the which portion of the brain is sensitive to which portion, how do they generate pulse on those things, right? So majorly, it depends upon the spot of light, the bar orientation. All this will be taken into account, and that has been given to the brain as a neuron. Now look at this. This is the typical human brain. I am just trying to project you very small information about this. In fact, there are many things in the human brain, right? You would have read cerebral, that is cerebrum, cerebellum, medulla oblongata, spinal cord, all this, more of biological information. But the point of our interest is only this smallest unit in the brain is your neuron, right? Which you call it as, here it is called as cortical neuron, because this portion takes care of the vision, this area, right? Whose size is more or less around 25 micrometer. You could understand one more thing. The human brain is being made up of 100 billion neurons. You just think about that. 100 billion neurons. And each neuron is being connected with the nearby neurons. The connections of each neuron is around 10 raised to the power 4. That is 10,000 connections. Means, say, let me consider this to be one neuron. I'm saying single cell of a brain, right? Right? Each and every neuron is being connected with the nearby neuron. The number of connection which it has is around 10,000. The total number of neurons is around 100 billion neurons. Now, I am just equating this with an IC. The IC number of MOS transistors is roughly around 10 raised to the power 10. Right? In fact, they let us to process the total MOS transistor count. If you look at, it comes to somewhere here. The neuron count is multiple times more faster. I mean, multiple times higher. The second thing, the neurons of the human brain, their response time is in 100 microseconds. Whereas the IC chip which you have made, the human made IC chip, can respond even to picoseconds. Probably, I think you might be those people who are in the hardware design might understand, like an IC processor which has been designed, they look for picosecond. Even even a couple of picosecond variation in the processor design could create a drastic change in their output, or no, a malfunctioning of the complete IC. So, in order to bring this sort of, no, I'm just equating human brain with the latest IC, right, with the transistor count and other. And one more thing, this human brain has a beautiful phenomena of parallel processing. Um, this you would have noticed something like this. While driving a car, you can listen to your music, you still speak with your wife, you still look at the front view and start driving. Your brain has an enormous computation power which has the capability of computing in parallel. But what happens when you take a CPU? The CPU operates in a sequential fashion. You could see the way it runs, or the execution of the instruction takes place in a sequential fashion. If I want this to happen in, or if I want to increase the speed, what I generally do is I put them in parallel, right? You could see the whole operation will be done in parallel. That is what we do with the GPU. It's actually a parallel processing unit in order to compensate the speed of the brain, right? And one more thing, sometime you would have noticed here, if the brain continuously works, the people would like to have some sort of coffee or something like that. You call that as your brain get heated up. The same thing with respect to processor. If the processor works continuously, you could see that's what you call that as a power dissipation, right? Very similar phenomena, that happens with the brain also. The whole idea is, what I'm saying is, the complete the human brain activity I'm trying to capture inside the chip. Correct. So I'm just trying to capture a single neuron, typically a single neuron. In fact, there are multiple information relevant to this single neuron. I'm not going so detailed based upon the time constraint. I'm just restricting myself to the important ideas to give you a quick go through. These small no branches like structures are called dendroids, and the center portion is called as a nucleus, and surrounding this you have a soma, and this lengthy portion is called as an axon. Usually, what happens, right? Um, any input that has been given will be given through these dendroids. Or here, what do I mean by input here and pulse? You need to understand one more thing. Actually, all your human activity or the brain activity takes place through some sort of electrical signal. You can't believe. Actually, the signal which is generated in the human brain moves from minus 70 millivolt to 30 millivolt, right? You can see the spikes for every excitation impulses which you provide from the externally, that could create an equivalent spikes whose amplitude and the frequency and the variation of the pulse can switch over from minus 70 millivolts to 30 millivolts. This spikes of information will be passed from dendroids, and it will move through the axon, and further it get communicated. This output portion is nothing but again it could be get communicated to some other neurons. That's why I said every neuron is being connected with the nearby neuron, right? Not physically, it's a chemical connection. I will let you know shortly what is chemical connection or how it is taking place. Each and every neuron is chemically connected with the nearby neuron. Sorry, is it not audible? I get a. Can you hear me? Hello?
Okay, sir, no
Yeah.
problem. Carry on.
Oh,
Voice is
okay.
audible.
Okay, fine. Thank you. they are being chemically connected with the nearby neuron via more than 10,000 connections. So you could see how complex web network is being developed in the brain. In fact, if you open, I had a chance of going through the brain in IIT Chennai, not exactly human brain, of course, we could not, we have seen that, but we have not taken work on that. But the sheep's brain, right? So it's like a layer of information, a layer by layer. So each and every layer, it's a lipid which consists of as I said, thousands and thousands of neurons being interconnected via. So this concept you could see EPSP, excitatory post-synaptic potential. What does this mean? This is a very simple concept, as I said. Say, when you see something, let's assume that you quickly see a drastic incident like an accident which is happening just before. Immediately, or any sort of event, right? Let it be an event. You could see an immediate pulse will be generated from your sensors. The sensors may be eyes, nose, or your skin, whatever it may be. These sensors will generate this pulse, and this will be passed on through the nervous system towards the brain. Now, the brain neurons carry out these pulses, and this pulses is nothing but excitatory post synaptic potential. Post-synaptic means the mechanism by which one neuron is being connected with the nearby neuron and pass this information to the next neuron. Thereby, it get moved from one point to the other. It's again something like just to understand, make the understanding a little more simple. So, if someone nearby you start pinching you, right? If the pain is within the threshold limit, you normally don't react towards that. You just leave it. If the pain goes beyond the threshold, immediately your excitatory system and the whole system start responding towards it. Your brain says, oh, kick this fellow, right? So automatically that information has been passed on to one of your organs, and you start throwing the hands nearby the fellow who is doing that. That's a responsive action that is taking place. The same thing, I'm trying to convert that as a spikes or an electrical pulse. You could see over a period of time, this resting potential is minus 70 millivolt. If any sort of excitation which is being given externally, that has been given to the brain via some sort of sensory network, that will go up to 30 millivolt, and something greater than this threshold will play an impact on the decision making of the brain. Yes. Now the question is, how could you correlate a brain to an electrical system or an electronic system? How is it possible? Correct. Now, when I say that the brain is creating some sort of electrical signals, now the immediate question comes in: how could the brain could have the capability of generating a electrical signal? This you would have noticed if you take a battery. Mainly, the electrical signal is being generated by the chemicals like sodium, potassium, right? All this. So the same thing here. Every proton, every neutron, every neuron here in turn has two sort of potential. That is inside this neuron, outside this neuron. Whenever the concentration of sodium or potassium or chlorine or water level get imbalanced between these 2 points, then what will happen? The potential difference between this outer end and this inner end create a potential, or create a electric pulse. Am I right? Whenever there is a change in potential, and if you could connect that, that's what our electrical theory says. When there is a potential and you have a closed path in that, then automatically a current start flowing in my network. The same thing happens here too. You have a neuron. The neuron is surrounded by a membrane. It is a cell membrane of lipid bilayer membrane. The concentration between the liquid which is present inside that and the liquid which is present outside that, right? Whenever the concentration differs, then automatically there is no channels, ionic channels, which could flow from inside to outside. Whenever this happens, this excitation makes the ionic imbalance, and this will make sure that there is a huge amount of potential variation. Huge means I am speaking with respect to creation of that voltage, right? Mostly starting from minus 70 millivolt, 70 millivolt to plus 30 millivolt, you could get that potential. This in turn develop an electric pulse, and this electric pulse is again being delivered to the nearby neurons, and this makes a collective decision in the brain. Right. So the whole story is being said over here. You could see somewhere this is at an resting potential. This is 0 millivolt. This is minus 70 potential. Whenever the potential concentration of these chemicals right changes, this lead to this is called as an ionic pump. This lead to the creation of voltage. In fact, there are a couple of papers being published on modeling of neuron behavior in the electrical circuit. I'll just quickly show you at the end. I mean, there are a couple of slides to do that, which will show you how can an electrical circuit be created from that. Yes, right. So typically, this is the electrical pulse which is being generated in every neuron. Actually, this is called as an action potential. Action potential means the potential which has been created inside the brain neuron cells for every variations that has been created due to the sensory cells of a human body, right? Okay. So you could see there will be a small spike and coming down back, right? So this variation takes place whenever there is an open in the sodium channel, and this no downfall of the potential will take place whenever there is a change in the potassium channel. In fact, there are many theory behind it. I am not going so deep into it, but in fact, there are many papers also being published in this of converting this to whole idea into an electrical circuit. Right. So this is the whole story. Sometime if you read some of the neuromorphic paper or some paper which are trying to work on this neuromorphic computing, you could see this synapse. Synapse is nothing but one neuron getting connected with the other neuron. One point you need to remember here is they are not physically connected, rather they are being chemically connected. They are called as neurotransmitters. Means the chemicals, what are the chemicals? Basically, the sodium, potassium, chlorine, water, and some sort of fume moving from one neuron cells to the other neuron cells. This is called the transmitter, this is called the receiver. Whenever this potential changes they happen, then this is equivalent to transmitting information from this neuron to this neuron. Or this is same as a spike transmission from this point to this point. So one neuron being connected with the other neuron. This is what you could see. Neuron 1 is being connected with neuron. By seeing this picture, you could see it is something like very fantastic figure. You could see at the bottom it is from the Kennedy lab. It's a real image being shown over here. This image is being recorded from a neuron, brain neuron, based upon the activation. So they have highlighted those portion of the activation potential. So you could see how interestingly they are being connected. A small portion, in fact, this is a very small portion of the brain cells which has been interlinked, and the neuron connectivity based upon the potential variation. So the same story, like one is trying to connect with other. Something like what is called as presynaptic, postsynaptic. What does that mean is, presynaptic refers to the potential before transmitting the information. Postsynaptic refers to the potential after transmitting the information via synapse. Synapse is a mechanism of transmitting the neurotransmitter chemicals from one neuron to the other. This is what you call it. Sometimes it could be an excitatory, and the other time it could be an inhibitory. Means sometimes say something like this. How do the brain learn? This is interesting portion of this, right? There are many studies, right? So we keep on learning cycles, bicycle riding. A couple of times when we practice, our brain start learning it. How does the um, real learning takes place in the brain? That's what we would like to know. Actually, this happens based upon the synaptic plasticity. What do you mean by this? Very simple. Look at here. Let's assume that there are two neurons. This is called the Hebbian plasticity rule. If one neuron is being connected with the other neuron, and this takes place multiple times, say something like this. First, I take a cycle. Uh, Assume that I don't know how to ride a cycle. Then, first time I take it, I fell over. Second, I understand there are some of the things which I need to follow. I start practicing for the second time. I learn a little bit. I correct the mistake. And again, I redo this for a couple of times. Automatically, right? What happens now? Your brain has activated apparently in all mechanisms such that you can ride a bicycle. Or indirectly, what is happening in the brain is the connection between one neuron and the other neuron gets strengthened, right? More the strength it has been made, then, right, what makes is it becomes an easy process to do that particular job. That's what you call it a cell. Neuron that fire, neuron that fire together, wire together. What do you understand by this? Say it's actually something like this. If I say I know how to drive a car, it's actually what has happened is your brain neuron has made an appropriate connections, and the connection has strengthened. Like on a path, compared to the remaining path, you could see that particular path would have been well established, right? The same thing happens with respect to brain also. When I say I know how to drive a car, out of the whole neurons present over there, the mechanism by which I drive a car, those neurons get strengthened up, well connected. So it becomes a habit, and that's what we learn. That's what we mean by learning. So let's take a simple example. If it is a first time, I'm trying to transfer an information from neuron A to neuron B. If you do this for a couple of times, right, then this neuron is being connected, well connected with neuron B, which means I understand that this is the way this particular job need to be done. So this is what you call it as learning. Or actually the brain learning takes place via this mechanism only. Any activity which happens, right, generally takes place by this mechanism. So it's typically this mechanism. Neuron that fire together. Fire together means connected via this firing in the sense passing the signal from one neuron to the next neuron, electric potentials, right? They wire together means they are being connected in order to do a job. That's how the neural brain activity takes place. So you have a long-term potential, short-term potential. Means when a learning is take place, you could see. I am just speaking with respect to electrical concept. You see the pulse which is being generated here, right? So day by day, or the number of times which you do that, which makes you to strengthen the pulse. This is called long-term potential, LTP, right? So more the time you do that, this process gets strengthened, and you get an electric potential or a pulse or a electrical signal with higher intensity. On the other hand, you have long-term depression also. Means you could see the difference. Initially, you had a no the electric pulse to be very high, and it start uh, no, diminishing, and the pulse become very weak. This is what you notice with the people of uh, age-old people. When the people crosses the age of somewhere around 80, 90, you could see they cannot hold the information for a long time, right? They will speak, they will recognize you and speak for a few minutes, and after some time, right, they forget everything, right? Because most of the neuron cells start dying out after a particular age period. Means their interconnections has a mislink, or they have a discontinuity in the linking of neurons. So thereby what happens, the potential keeps on degrading, and you may not be able to do that, or you forget quite often. I still remember there is, I mean, there was one person around 94 age in my village, and I was meeting him. He knows me very well. I am speaking to him. After around 2 minutes, immediately he started asking, "Who are you?" I again start introducing. I am Sakthivel, son of Ramachandran. Okay, then he said, "Oh, he is a nice person." After 2 minutes, then immediately he was posing the same question: "Who are you?" This happens for every 4 and 5 minutes, right? So he could hold the memory only for a period of around 4 to 5 minutes. Beyond that, the neurotransmitters all both fades. Okay, so this is for long-term depression. It keeps on decreasing. Not only in that case, not only age as a factor, it happens with multiple cases. Even if you fail to recollect certain incident or some concept, that keeps on decreasing, and you could see this get down. There are, if you go through some of the IEEE papers, you could see this important concept. Most of the papers would have been discussing on. For the want of time, I'm not entering into that paper. At the end of the session, I will show you some of the paper which we were working on. You can also go that. How do this, the research work going on with this? Like, based upon the synaptic plasticity. Plasticity means the way it has been connected, uh, and based upon the timing, spike timing, right? Uh, how long and the duration of the spike, all this matters a lot in deciding what sort of connections has been made, how, whether it is this LTP or LTD, all this. I'm not going so deep into this. Probably there are many theories behind it. We will, for the want of time, I'm cut shorting everything. There is one more concept called as spike timing dependent plasticity. In fact, you could see STDP. There are many papers being published. There are many circuits, VLSI circuits, electronic circuits has been done in order to mimic this behavior. Spike timing dependent plasticity means how the spike is generated, and whether the spike is generated before the input or after the input. How are they being done, right? To do this, how are you going to create a circuit for this, right? Something like hardware to mimic this timing dependent plasticity. There are many circuits. In fact, there are many research papers being published in this area. If you just Google it in the IEEE area also, IEEE journal papers, you could see STDP. There are many papers which have been. Okay, right. And again, I'm quickly moving ahead. There are three types of learning, like supervised, unsupervised, all this. In fact, you train your brain neurons in order to make some sort of classifiers, right? You decide, say, you show some 100 chairs or 2000 or 200 chairs, and then keep a new chair which is not belonging to that particular model. You will say that the brain will say it is a chair. How does it capture? You have already recorded the input and output, right? So based upon that, you make your brain train. Yeah, okay, a chair should have a 4 legs, and so on, so futures. All this you have already given the well-defined future of the output. That's what you call this a supervised learning, right? Particularly with respect to face recognition. If I could show all this and say, my brain, you detect which are the face, then immediately my brain will detect that these are my face, these are the faces, and all the other things are not face. This is a binary classification being made by the brain. To do this, in fact, you have an the pakka electronic circuits, right, with gate level electronic circuits to execute this particular problem. Means you create a hyperplane and you decide. So these are the things which is a face. These are the things which is not a face. When it is a face, you give one. When it is not a face, you give -1. You make a binary decision about that, right? So how do I get it, or how do biologically what is happening? Again, the same thing. It is something like this. I have a these are the n number of input which is coming over here. the W1, W2, W3 are the weight. In fact, it is mimicking the strength of interconnection made with the subsequent neuron. Say one neuron is having some 500 connections. The other one is having some 200 connections. So based upon this, a collective inputs which I get it, I just make a decision. The decision is binary, means okay, if this crosses this Smith threshold, I decide okay, it is going to be my face or it is going to be a face. Else it is not a face. I am mathematically equating this. That is input multiplied by the weight minus threshold, right? Will make me to make a decision. If it is plus one, I do say that this belongs to this particular category, else it is not belonging to this particular category. In fact, this is for a single thing. This is what you call it as a perceptron, single perceptron. In fact, you could again, this take place via an iterative process. What do you mean by iterative process? Sometimes you do a wrong classification also, then you make a correction. Then how do I correct it? You find the difference between those two. That's what you call it as a mean square error. I believe those people who are doing machine learning might be doing this. Get the difference of that two, make an average of it, and then square it to get away from the positive negative sign. Thereby you get a single perceptron. This is called perceptron learning rule. I'm not going so deep into this. This is the very basic of the learning which is taking place. Again, in case if you cannot classify them as a uh, two plane. Okay, I will do that. I am supposed to enter that portion. Maybe after doing that, probably you could understand. How could I? How could I make this say something like this? If I want to make a classification for an XOR, so this area you have -1, this area you have +1. In fact, you need to segregate using two hyperplanes. I cannot segregate into a binary. Uh, no, yeah. Um, what is this? Uh, and a decision which is being made either true or false. It's not like that. Rather, it's a linear decision. Say, let's assume like this. I want to buy a house in the Chennai city. So it's not like a single parameter which is deciding. There are multiple parameters which I need to take it. This is what you call it as a regression. Based upon change in this all this parameter, I find what could be the change in the delta y, right? Something like more on the mathematics. So if I incorporate those things, then it means that it is a linear separable model. Then I cannot make this decision based upon a single perceptron. Rather, I make it with multiple layer because my decision is being made based upon multiple parameter. I need to process this within multiple layer. Or simple example, let me assume that I want to get a color painting for my house, right? It's not green, it's not RGB, it is not from any of these RGB colors. It is a composition of three different colors. So how do I do this? I go with an iteration, but that color as combination has not been mentioned to me. Say, let me assume that I am going to paint my house with a color combination of 10% green, 20% red, some 30% RG blue, right? 10, 20, 30. Now, I have given that output alone. This is the paint which I use for painting my house. Now, I want people to find out what is their composition. So, what they will do? They will take this input as RGB. They go with all possible iterations. What is that iterations? Red being 20, green being 30, this being another 40, something like that, in order to make a 100% composition. They go with all possible combination of mixing and see whether this particular combination is same as the color, destination color given by me, which I used for painting my house. It is not purely green or blue or red, rather, it is a composition made on different colors. So I go through multiple iterations with different compositions of different color to do this. So I cannot make this as a single perceptron decision. it need a multiple decision. This is multi-layer neural network people used to call, right? When once that color matches, then I fix out, oh, these are the combination 10, 20, 30, so it doesn't count to be 100. Okay, now let's make it as 30, 30, 40. So this composition should be given for these colors so as to get. But this happens over a huge computation, right? Enormous computation that need to take place. Right? The same thing which happens, most of the cases, it is not a bilinear decision, either 0 or 1. Sometimes it is a continuous process. That's why at the end of decision making, you could see in the neural network, there is a function called as decision making function, like sigmoidal function, tan x function, right? And you get multiple ReLU function. All this, they helps to make a decision where your output is not a discrete decision, means 0 and 1. It is a continuous output. So say something like sigmoidal function will go by this rule, 1 by 1 plus e to the power of minus x, whereas tan function e power x plus, sorry, minus e to the power of minus x divided by e power x plus e power minus x. I think the people who are doing the uh, no, neural network might know all this. But the thing point which I want to mention here is, where does the VLSI circuit comes here? In fact, if you search in the IEEE paper publication, you could see there are n number of circuits being published as a paper only to model the tan h function, sigmoidal function, or something like ReLU function. Just to do this alone, there are multiple research works being done to construct a circuit to do that purpose, right? For the sake of time, I'm not showing all those papers, but you could in turn go back to any of the journals, IEEE, Springer, elsewhere. You could collect all these papers on this area. So this is again, a single layer cannot make a decision. What we do is we go with multi-layer perceptron. This is what you call as deep neural network. If there are more than one, except the input layer, output layer, if there are more multiple layers, right, that you call it as more deep neural networks. Particularly deep neural networks, RNN, CNN, all this plays an important role, right? In fact, there are many papers, I will show you at the end, being published in the area of CNN. If you just type hardware for CNN, right? In fact, there are 2 to 3 BTech students. They have done efficient hardware for CNN networks, right? Convolution neural networks, which is used for machine learning. So that could also be done. Right. So ultimately, the idea behind the whole thing is, I am trying to reduce the error. Well, this is what you call it as a gradient descent. So if you go through the video lecture of deep learning by Andrew Ng, or some of the standard books, you could see the complete mathematical analysis being done in the gradient descent. So whenever you differentiate that equation of the error and make that to 0, you will get the least amount of error. So basically, the idea is to predict what should be the next value, what should be the appropriate weight and the bias that need to be given in order to decide. There is some sign. Unsupervised learning, it is something like this. The main difference between supervised and unsupervised is something. Say I do like this. I define this. Sorry, someone would like to interpret? Okay. So please switch on, mute your mic at your side. Okay. Right. So what I'm trying to do, unsupervised learning, mostly this machine learning happens with something like this, right? You are not going to say anything on the output or the features of the output. Say something like this. In the supervised, I will tell chair. If I say chair, it need to have 4 legs, and it can have or it may not have the the slanting side at the back side. The height will be somewhere around 3 inches, almost near to your elbow, or it may or may not have a cushion, sitting cushion. Like this, I can give you a long list of description for a chair. But so now, if I give some input, it will cross check with that, and you have already given all the futures. It will simply check and then it will say. But when I say unsupervised learning, I will never say anything about what is the output. I will do like this. I will collect, say, some 2000 different shirts that could be possible all over the world, and give this shirt as an input for my network. So what it will start doing, it start extracting the futures of each and every shirt. This is what we call it as self-learning. You make a system to extract the futures from this 2000 or 2000 variety of shirts, and this will be kept as its future. And whenever you give a new one, you try to see whether my input is within any of this 2000 no shirts which you have given that as an input. You would have extracted some of the future. You simply cross compare and then decide. It goes for clustering. It belongs to shirt category. It belongs to trouser category. Something like that. It's not classifying this. So that is the major difference between supervised learning and supervised learning. Again, remember, there are many circuits for unsupervised learning also. For the want of time, I am not touching that there are many circuits. In fact, this I am simply trying to give an electrical equivalence of a brain model. Right? This is also available as a paper, and it is also available in your book, that is Dayan book. Very simple. By this time, I think you yourself can identify how could I model my brain. So if I consider this to be the brain neuron, outside potential is different from inside potential, then you could see I can, whenever this potential varies, the conductance that happens, right, will take place. How it will take place? Whenever two potentials or two opposite charges separated by a space or a dielectric, it can be equated to a capacitor. I believe you know this, right? So the charge is Q equal to Cm. What is C? C is the capacitance. V is the potential, that is resting potential. Now, if I differentiate this dq by dt, that's my current, right? So Cm times dV by dt. When can the potential difference take place? Whenever there is an electric current, whenever there is a potential difference that happened due to the current externally being fed, the ionic concentration between these two layers get different. That immediately lead to the variation in the potential. So this becomes the basic current. If I want to model this neuron behavior, it is something like this. You have a capacitor, you have a resistor, you have a resting potential of E. You can apply Kirchhoff's current law, voltage law towards this and differentiate it. Then you will get a pakka equation, something like this, right? If I am differentiating this, you will get, multiply both the side by Rm. So this Rm Cm is nothing but, this is for a membrane, right? Rm Cm is nothing but a time constant. R and C are the constant for that particular neuron membrane. So that becomes the time constant. So tau m. So dV by dt. Then you can simply equate this to an equation, V minus dVt plus IE times of Rm, which otherwise you can also equate this Rm by 1 by Gm. 1 by Gm, it is transconductance of this particular device. So they have created one model, a couple of authors has created, and they made a study too. In fact, this is the equivalence of the operation being performed inside a membrane to membrane, right? I am just speaking about a small portion of the research where the people are concentrating only to model the neurons, right? I am not speaking about the high-end circuit level. I am just speaking about only the synapse modeling, right? So you could see, in fact, this happens to be one of the benchmarking paper which came out, that is called Huxley model. This model is very good model. In fact, the whole derivation, all those things are being done in this paper. You can straight away go to his paper and see the complete derivation made by him, and you could understand. He had also made some experiment to find out what is the potential for the sodium, potassium, all this, right? For one time, I'm skipping it out. In fact, there are two theories in the paper. One is spiking and the firing neuron models. And again, I'm skipping it out. The second thing is recurrent neural network. Very similar to CNN. There are two class of networks, right? Where you could see the people from the VLSI domain could see multiple papers being published. I will show you at the end a couple of papers which mostly myself and my students are working on. You could see there are two class of networks they work on. One is recurrent neural networks, RNN, and the CNN, the convolution neural networks. Whenever say something like this, a quick thing to differentiate between these two networks is when you want to classify an image, you normally go with convolution neural networks. When I want to remember something from the previous discussion and then respond, then I go with recurrent neural network. Means whenever I need to have a feedback, right? Whenever I need to remember something, I go with recurrent neural networks. Say, for example, right? I am reading a novel. So I am reading the third chapter of the novel. When I read the third chapter of the novel, it is implicit that I am supposed to know what has happened in chapter 1 and chapter 2. Then only it makes me to correlate with the third chapter or fourth chapter subsequent chapter. If I forget what has happened in the earlier and I don't have any idea about the previous one, then it becomes useless, right? So the output which I am supposed to, or the circuit which I am trying to come up, should have some amount of delay. For delay, I can create a circuit. Then a function. This function can depends upon multiple factors. Let me assume that it is a simple function. Probably this could be a differential equation too, right? So W and U is my input. W is my weight. M again is the feedback. Means say the one character name would have been introduced in the first chapter, second chapter. I need to know what is that character, right? So I need some amount of input from the previous, right? A feedback, present input. It's something like a sequential circuit. To be the people who are working with circuit design may quickly understand it's nothing but a sequential circuit network. Whereas on the other end, you could see a combinational circuit mechanism can be used for something like a CNN neural networks, right? There, I am just going for classification. It need not have a memory, or mostly it is more towards coming up with more on images. Whereas this is for voice track recording, voice identification, all these things. This recurrent neural network is being used. And the reinforcement learning, this I have already given a hint over that. Means I just look for some of the circuit which could have a training that will give you a reward or something like punishment. Conditional stimulus. Say for a simple example, look at here. One experiment was conducted. A dog was there. At every time the bell ring, the food is being provided. Right. So under that case, when once the bell ring, the very well that the enforcement learning, there are many research works going on in this area. I am speaking about the hardware, right? There are many papers which has been published in this reinforcement learning, and it is more effective method of learning, which comes out with the reward, how to create a circuit, things like that, right? So I am abruptly stopping here because the time goes out, and I am just going ahead with some other paper at the other end, because yeah, I could see there are some questions being raised where um, the hardware is being used. Yeah, the next portion what I am planning to do is, like, how could you go with the hardware making. I am not concentrating more on that, believing that the last 2 days, since there are more discussion on like FPGA based system design, I don't know whether those portion has been covered here. I quickly skip out for the simple reason, maybe it would be a overlap. Or if I am starting that complete VLSI design for these type of circuits, then this itself will take me another 2 3 hours to make you the complete flow to get in, how to model a system in your electronic circuit as a digital system, how to model that using a HDL code, and then how do you take that to the circuit synthesis, then how do you fabricate that, how do you test that, then how do you validate this based upon the metrics. So this oh, someone is asking for the dog and the dog. Okay, I will do that. So that process is cannot be done within the short span, but maybe in the I am planning to have a separate webinar as a session. I mean, a series of webinar. Probably I am planning for some 10 hours or 15 hours. I am just putting out my mail ID. You can just put a mail to that. So probably I could consolidate that, and whenever I am speaking, whenever I am doing a next session, I am planning to do this, where it will go from start from the spec to till the end, complete hardware for any one of the system. Like it could be for a CNN network or RNN network or something like a research paper. We would like to take it and go from the top to bottom. Right? I am planning to do that. So I am just putting my mail ID in the chat box, or I will do this RSAKTHIVEL at vat.ac.in. This is my mail ID, and I am as an associate professor from School of Electronics Engineering, VIT Vellore, and yeah, my mobile number is 999 4627 570. Maybe you can just. I am planning to have a group. So possibly by this, if at all, if the college doesn't reopen by June 3rd, I may plan for some 1 week session. I'm planning for it. So I can just put a message to you all. You can just ping me a message to this mobile number so that I could consolidate a group for this area, and I will pass a message to you all. So thereby you can again follow it. So this is just an eye-opening session. I thought I will take you just to have a overall glimpse, because as I said in the beginning of my class, this is a multidisciplinary domain, and the expertise required behind all this is really very huge, and it takes a little bit of time to practice and confine yourself to work in that particular area.
Sakthivel sir, Sakthivel sir.
The dog brain has been trained such that whenever there is a bell sound, then it will think that, oh, my food is ready, I'm going to have my food. Automatically what it happens, the brain cell will activate all the salivary glands to salivate. So whenever when once the bell ring, so it understand that I am going to get a food and the food will be served to him. Sometimes if you stop that also, you could see the saliva being running around in the mouth of a dog. It's same as like in the hostel. So whenever 8 o'clock, so you can go for dinner, something like that, or breakfast. You have your mind is being trained towards that. Means you are getting a reward at the other end. So if you do some mistake, you'll get a punishment. That is again an indication that your brain trains you to get a reward or a punishment based upon some activity. That's what you call it, a training. That complete mechanism is called reinforcement training, learning. This take place. There are multiple papers, experiments, and some of the research work being carried out. Again, I want to make one thing very clear. um, there is an equivalent way of discussing the same topics, whichever I said, like RNN, CNN, all this. Simply, I mean, not simply, in fact, in the different track, like computer science people, they would like to go ahead with, um, going with the ML algorithms. So you could include all the uh, program codes which is already written in Python, or you will be running that, and you could see the classification, all those things will take place, right? But I'm not concentrating more on that computer science portion. Rather, I'm just taking you to the hardwares that will be equivalent on the other way, right? Just to make to have a glimpse, I will just show you some of the papers, just to make you that how the papers are being published. Could you all see my screen? Someone please respond. I have just opened the IEEE paper. Could you see that? Yes. Thank you.
Yes. Yes, sir.
Yes. You could see one paper which is on digital CMOS neuromorphic processor design featuring unsupervised online learning. This is typically the paper will go through by taking different layers as my input, the architecture, then the appropriate weight, the computation, the circuit required to do that computation. Here you could see it is being made on spike timing dependent plasticity, STDP, right? I have just given more of the input session only. I mean, the overall idea only. I have not gone through more of technical details of the paper designing, right? So there is one more paper you could see here, a reconfigurable neuromorphic VLSI multi-chip system design applied to visual motion computation. This is more like used for visual images, computations, all these portions. And you could see one paper. I'm just giving only the latest paper, which some of the paper which has been doing by my present student. This is in September 2019. Low cost, high speed neuromorphic hardware based on spiking neural networks, means the hardware spiking which has been created. You could see there are how equivalent hardware has been created. How are they being computing? What is the architecture for the computation? So their metrics like area metrics, LUT metrics. I believe the last two sessions you would have know what you mean by LUT, what you mean by slices, what you mean by how the maximum speed, critical path, power, area, PDP, EDP, all these metrics become so important. I believe you might be gone through those things in the last two classes, right? I mean, 2 days of the earlier session. So that's the reason I have skipped that. Otherwise, I would have gone through that also. So these portions are different standard benchmark work which has been done by different people, like this ABC Rich, then edX. These people has done a good, remarkable work in the VLSI with respect to different modeling and the hardware architectures for the machine learning things like that, AI also. And this paper is for a compact VLSI conductance based silicon neuron, that is equating the behavior of the silicon, right, in a VLSI circuit. Here also you could see a complete CMOS circuit that have been done. Again, I'm skipping up for the want of time. So here, a low power tunable neuromorphic integrated circuit that is tolerant to device mismatch. This is also one of the IEEE paper which has been published in this area. And this paper is on stochastic computing. Of course, I haven't touched this part. Means a huge amount of mathematics, particularly statistics, is being involved while it comes to predictions, right? Prediction, estimation, all this. For the want of time, I didn't touch up on that particular portion. That is more on data science, right? And how do that being used for creating an efficient VLSI circuit for it. And here, an analog neuromorphic coprocessors that uses device mismatch for learning application. And one more thing, this is with large scale neuromorphic spiking array processor design. This is to mimic the brain, right? A quest to mimic the brain. It is also a good paper in the neuroscience, the Journal of Neuroscience. There is a separate journal for neuroscience. And a couple of paper again, low power neuromorphic analog system based upon subthreshold current. There's one paper which has been done by one of my student based upon this paper he has also done. And one of my PhD students is also working on this in the subthreshold region. The subthreshold region, how do they use memrest for brain memory, like that also. So all this completely, how to do this or how to analyze this circuit, how to simulate this circuit, how to synthesize this circuit. If it is a digital circuit, what you need to do. If it is an analog circuit, what you need to do. What type of tools you require. I believe the last two sessions would have highlighted that, like cadence, graphics, or tools like FPGA tools like Altera, Xilinx. All this again plays an important role in deciding that, right? So some students who are doing projects on this particular area, particularly this is a very booming and interesting area where you could come across with multiple projects, right? And for I have just shown you only a few, around more than 600 papers within the last 5 years I have in this particular domain, right? So you can collect papers from IEEE, Springer, elsewhere, all that. I believe this those people who are yet to start their PhD work or things like that, if they are interested and they do have some idea about circuits, right? Digital circuits, analog circuits, some amount of knowledge on that, and would like to pursue their PhD in this domain. I think this area is really a beautiful area to work on. Professor Arun, okay, I think I can take a couple of questions. Yes, I can take a couple of questions.
Okay, sir, carry on. Sir.
Yeah. If there is, please share the last 3-day material. Okay, that's fine. Abstract, keywords, introduction, literature survey, proposed methodology. Talking of, I don't know. This is the steps. I don't know what for this question is being raised. Is there anyone who share all the PPT? One problem with this PPT, I will try to share this. Couple of slides, as I said, I have taken from only those people who I have given the credit. I don't know whether I do have the right to do that, because it's there. Some of the things are literature works of, not literature, experimental works of those people, and some are from the labs. I don't know whether I could share all, but something which is pertaining to me, I can share it. That I have the rights to do that.
Sir, can we implement a neural network, that is machine learning network, in VLSI using MATLAB and Simulink?
Exactly. Yes, you can do it. Actually, most of the cases both goes in parallel. Some area we will be using MATLAB, and some places you will be using hardware. But what I'm trying to say is, if it is your research point of view, you can validate your results with MATLAB or using Python. You can even go with any of the ML tools which you can use it as usual. But the hardwares will be done using, like if it is an analog circuit, you need to go ahead with the cadence transistor level design. Or if it is a if it's a gate level circuit, you may go with either with the FPGA or ASIC, starting from your HDL coding to simulation synthesis. Then that will land up with an IC, right? Something like, I think I'll show you. I don't know whether is there any paper with processor. One minute. Finally, the end output will be something like this processor. If you would have worked with, I will also show it here. They would have end up with an IC which is completely having all the spec of area, power, timing, all those details. So that will be still more efficient, and the acceptance of the paper, all those things get increased.
Okay, sir.
Some of the papers have that. Yes.
Okay, sir. Another question is whether Python is better or MATLAB is better for machine learning.
I think there are more library with the Python other than MATLAB. It all depends, but most of the I tried something with the Python. So here you could see the I said no. This is a simple circuit which goes with the layout of one conductance. This goes till the back end. Can you see here? It's typically a VLSI circuit where they have gone up to the layout, a single neuron.
Okay. You have used that Spartan and all that for downloading? Spartan
Sorry. Yes,
Uh,
yes. You can use either Xilinx or Spartan, D2, from Altera, anything. But only thing is, make sure that the size of the circuit which you are going to download, that should get accommodated with the board which you have. Normally for CNN network, for a very high CNN network, I think one paper was there with CNN network. I don't know whether I have here. That are from my students. So for that, there are very huge requirement of computation. So for that, you need to see the number of CLBs which you have should be definitely higher, right?
Okay.
So that alone you need to take care. Otherwise, anyway, you are going to do that for n number of times. If the computation goes higher, you can appropriately change it. So this is one paper you could see, CNN only with respect to hardwares. And in the CNN, you have latest, I think in 2020, there was one paper for efficient CNN networks, IEEE transactions.
Okay.
That was also very nice. Yeah.
Okay. Thank you very much, sir. Thank you.
Thank you. Yeah. Any more questions?
Hello, sir. Good
Yes.
evening, sir.
Good evening.
Sir, I am Jean Shilpa, sir. I was a student, sir, way back.
Oh, Jean Shilpa, how are you?
Yes, sir. Sir, actually, you were actually handling analog integrated circuits for us, sir.
Oh, yeah. Thank you.
How was your? How did you get interest to switch over to this speed, sir? And what made you to start working with CNN, sir?
Yeah, actually, I started, to be frank, last 3-4 years. There were couple of works being done in IIT Chennai as well as IIS Bangalore. That is a separate team. Those people who might be following this might be knowing that there is a separate team called as Brain Inspired Computing, both in IIS in Bangalore and IIT Chennai. They conduct some 10 days or 7 days, something like that. 1 week, a regressive workshop which is being done with renowned professors who are working in this particular neuromorphic computing all over the world. Beautiful workshop. So last year too, it has been done. Every year it is being done. So don't miss. Usually it comes in the month of Jan for IIT Chennai, whereas for IISc Bangalore it is being done somewhere in July, something like that.
Sir, if you can arrange for FDP like for beginners like us, we can
Yeah,
start
sure.
learning, sir.
Yeah, I can share whatever I know. Not a problem.
Thank you very much, sir.
Thank you.
Sir, one question, sir.
Yeah.
So if we implement a neural network using CMOS circuits,
Yes.
how do we validate the results?
Yeah, that's what. It's actually yes. Over, or you
Yes,
want to add something
validate
towards
the
this?
results, sir.
Exactly. Yes, it's actually what is a neural network? If you make that, it is just an equation. Am I right? So
Yes, sir.
x into some weight multiplied, then with some sort of bias, then finally a function.
Yes, sir.
Okay, you
Yes.
just decompose that.
Yes.
If you decompose that, what is going to happen? One multiplier, one adder, or one subtractor, then one some sort of, if it is going to be a bilinear operation, then you can simply segregate using a comparator. If not,
Yes, sir.
I need to use a continuous function, as I said, sigmoidal or tan H or ReLU function. I can
Yes,
create
sir.
an equivalent hardware for all this function again. I'm simply
Yes.
giving you an example. So all this neural network, in fact, it is nothing but a conversion of an equation to corresponding a computational element.
Yes, sir.
This is with a single layer. If I say multi-layer, then obviously the complexity increases, and instead of a single unit, you have a vector. Now, I am not going to do a single multiplication operation, rather it is going to be a matrix multiplication or matrix addition, things like that. So completely it becomes a matrix operation. That's why I said, well, you go with the CNN network, right? There you require a huge matrix operation.
Okay, sir. Sir,
But
and one thing, sir,
typically the same process.
how do we
Yes.
train it and how do we validate the results, sir? We are
Right.
just working on it. We got the output, and the output is okay for a single layer.
Correct. So
But how do we
training,
train it?
correct. Training actually, this objective is to develop an efficient hardware. The training algorithm, if you want to synthesize a hardware for the algorithm, as I said, you can go by the same process. Once you finished all sort of training, you freezed with the architecture, then I can go directly for implementing in a hardware. Now, usually in the computer science department, what they do is they use the algorithm, whatever may be the algorithm, they give some set of data for training and some set of training data for the identification of whatever test data, right? But the algorithm remains the same. Either you go with whatever type of algorithm, only the way in which it has been trained, it is equivalent to having a memory in your element, memory in your hardware, future extracting memory in your hardware.
Sir, but when we go for CMOS, how do we give a real-time input or how do we validate the result? All
All
these things are obstacles, no?
correct. No. All input are nothing but a bit matrix.
Okay.
It's a binary value.
Okay, everything
So
in a matrix
yes,
format.
yes. When you go with no, in the computer science domain, if you want to write a code in Python, you see that as some values. But in
Okay.
turn, what actually happening, you are feeding a matrix as a binary value. That's it.
Okay, sir. So I think you
All
remember.
pixel.
Okay.
Yeah.
So I think you remember me. I'm Malati from Congo Engineering College. I've attended a
Oh,
workshop. Okay, sir. Sir, and I
oh.
have some doubts to. Can I mail you or can I
Yeah,
mail
sure,
you?
madam. Yeah. You can
Sure.
mail me. Maybe we can have an offline discussion.
Yes, sir. I'm working on this with memristors, and
Oh,
I
great.
have so many obstacles there stucking somewhere else. That's why, sir.
Okay.
I'll just mail you. Okay, sir.
Yes, sure.
Okay, sir. Thank you. Thank you.
Sir, good evening, sir.
Good evening.
For detecting the neurons also, it is will be difficult, na, sir. When the person is sleeping or when the person is active, how we will capture the neuron?
Until unless there is some excitation, a stimulus, you cannot capture the spike generated in the brain. Means until unless there should be some sort of stimulus. So I need to see that visual option should enable the optical nerves, and that data need to send to the cortex of my brain. If there is no stimulus, means there is no input to the brain or the sensory organ, you will get only that minus 70 millivolt, which means that it will not. It is in the it's the rest potential. It means the brain is not doing active job. There is nothing to decide on that. Say I give one object, right, and I am saying to detect what is this particular object. Then actually you are simulating your brain. You are given a job to the brain of the opponent to find out what is this. Now your eyes act as a sensory organ. It capture all this information, and there is LGN, lateral. There is one portion in the brain which will capture this information, and this information is being sent to B1 cortex of the brain, right? Peripheral cortex B1. That area is responsible for converting all the information regarding the visual cortex. So that will create an appropriate spikes in my brain. If that get matched with the already recorded pattern of your brain, then it will say that so this particular object is so and so. But if you don't give any stimulus, you are not actually activating any of your brain. It's going to be an idle.
Sir, is there any books, reference books, or some synopsis type something is there, sir?
Yes. Maybe I can give some of the reference books. I can pass it on to Arun. As I said, I can.
Yes,
do
sir.
Okay.
Yes.
Yeah.
Okay.
There's many books and many papers also. Yeah. Okay. It was. Yeah. Please.
Sir, what is the difference between CMOS logic designing and switch level modeling of HDL programming, sir?
Okay. So it's more on the designing. As I said, if you want to model a neuron, mostly the papers which has been published, it will deal with something like transistor level modeling, right?
Yes, sir.
You could say almost most of the structure would consist of current mirror, current input pulses, balancing, mismatching, or any excitation pulse which comes out of it. So based upon this, most of the circuits would have been designed. If I want to model this circuit, or if I want to simulate this circuit and get the response, I need not run any HDL code. Remember, right? This is a switch level circuit, means transistor level circuit. It is quite enough. You can use Tanner or you can use Cadence Synapses. Cadence Virtuoso will support this. You can simply draw the circuits for that in the Cadence Virtuoso. Give appropriate test input, simulate and check it over. That you can do. Whereas if I speak something on this, like CNN network, RNN network, here I am just modeling the functionality of the brain, like classification, detection. I am not going to model a neuron. It is the functionality of the brain for a particular job. And in that case, it is still more higher level of abstraction where the job will be done in the gate level. So sometimes it could be a sequential circuit, sometimes it could be a gate level circuit. So for that you need a HDL. And again, implementing that may go ahead with either FPGA platform or it could be an ASIC platform.
Sir, one more question, sir.
Yes.
Sir, you'll be getting a synthesized netlist from if you go with HDL coding.
Yeah.
So again, can we optimize that synthesized netlist also?
Yes, the synthesized netlist can be optimized, but the optimization takes place with a different objective. Say, I want to optimize with respect to speed, or I want to optimize with respect to power, or I want to optimize with respect to testing. So the purpose defines what sort of optimization you are aiming for. This will take place in the script while you write a script. So generic optimization will be generally done. Either you go with ASIC or FPGA, you can get a synthesized generic, say it will say this much amount of gate, all those things. But when once you say,
Yes, sir.
I want to optimize with respect to multi-VT, or I want to optimize with respect to boundary scan or something like that, then the synthesis process will appropriately change according to your need.
Yes, sir.
Yes, that could be taken care in the scripting, in the synthesis scripting.
Okay.
Yes.
Uh, Sir, can I ask one more?
Yeah, go ahead.
Sir, I think can we use Tanner tool, sir, to do the paper publications in like SCI index journals?
No issue. You can use it. That's not a problem. But generally, we could see most of the people will stick on to cadence, sometimes synopsis. But nothing wrong with Tanner also. No issue.
Okay, sir. Thank you. Sir.
Yeah. Any more? Last question. Okay.
Any participants want to ask the question? So thanks all the participants who are actively participated in this 3 days.
Thank you, sir.
Anyhow, our
Thank
HOD
you,
sir will be
Sakthivel,
conveying the
sir.
validatory address.
Thank you. Thank you. Thank you.
He will be conveying that thank you
Can you
message.
pass the
And
information if you conduct
HOD.
the webinar or workshop, sir?
Participants,
Yeah,
please
definitely. I have given my mobile number. You can just ping me. I will form a group. Probably I will include it. Okay.
Sure, sir. Thank you.
Thank you.
Yeah, good evening, one and all. I am Dr. M. Nageshwarao, Professor and Head of the Department of ECE, GMR Institute of Technology. At the outset, I would like to congratulate first Dr. Arun Shekhar for coming up with a good workshop titled VLSI Technology and Hardware for AI and ML. I can understand that level of the topic. Within 4 hours, we have got a only initially planned for 100 people. So first day we have started with Cisco WebEx platform for 100 people, but there are tremendous pressure and requests from several participants. So we tried to do the same through screen the same content through YouTube live streaming. But there was a problem in that audio devices is not compatible with that, so sorry for that. But today I hope you might have enjoyed the session without any
Yeah.
interruption.
Yeah.
On behalf of management of GMR Institute of Technology, I would like to express my sincere thanks to the 3 days resource persons. First day, Dr. Nirmal, HOD, ECE of Karunya University, and he is also a senior IEEE member. And Dr. Ajayan, Associate Professor, ECE of SNS College of Engineering and Technology, Coimbatore. And today's speaker, Dr.R.Sakthivel sir, Professor, Senior IEEE member, School of Electronics, VIT, University, Vellore. I'm very happy to say that we have received excellent feedback from all the sessions except that audio problem on second day. Anyway, it was not unplanned, only based on the request from participants. We have extended that facility. And I am express my sincere thanks to all the 3 eminent resource persons for sparing their valuable time with us and sharing their expertise in the field of VLSI and hardware for AI and ML to all the around 400 to 500 participants who were benefited with this. And also I express my sincere thanks to all the participants for their patient listening and cooperating with the schedules and all. And I hope that the 3 day sessions you might have enjoyed, and some takeaway might be there with that. I think with these 3 days and 3 sessions we cannot get anything. Whatever we have learned, that we need to extend it in future. That will be only one request from my side. Finally I would like to thank all the people whomever directly or indirectly involved in making this workshop a success. Thank you, one and all. Thank you.
Thank you, sir.
Yeah, as far as the certificates are concerned, several people are sending the messages through the software. We can send only 100 certificates per day. Definitely those people who have attended the 2 sections, you will get the certificate. No need to worry. After 7 days, if any certificate is not received, any participant did not receive the certificate, you can approach Dr. Arun Shekhar. Definitely, if you are attending means, definitely you will get. We will take meticulous care in sending the certificates. If not, anywhere anything is missed, please feel free to give a mail to Arun Shekhar. Before 7 days, please don't ask, don't be in hurry. Definitely we'll share the certificates to you all. Thank you.
Okay, thank you, sir. Thank you.
Thank you. Thank you.
Thank you all your participants. I'm very much thankful for all of you joining this 3 days on the faculty development program. I once again thank you all the participants and today's resource person, Dr.R.Sakthivel. I am ending the session. Thank you all.